Welcome everyone. Today we're going to jump way past the simple train test split. We are going to build a really powerful framework for evaluating our machine learning algorithms with some actual mathematical rigor. It's all about turning a technique we all know into a precision tool.
So let's kick things off with a problem that I bet hits close to home for a lot of you. You train a whole bunch of models, you pick the one with that amazing score on your test set, its performance looks fantastic, but then you push it to production and it just completely falls apart in the real world. So what on earth is going on there?
Well, it turns out this isn't just bad luck. It's a real statistical thing called the winner's curse. You see, the very act of picking the best model from a group makes it super likely that its score was just an optimistic fluke. And this is exactly why we need evaluation methods that are way more robust than a single performance score.
Okay, let's dive right in. Here's our game plan. First, we are going to add some much-needed rigor to the good old holdout method. Then, we'll figure out what cross-validation is actually trying to tell us. After that, we'll challenge this idea that all our data is the same, look at how to evaluate models for the real world, and finally, learn how to build a truly honest evaluation pipeline.
Right, so we all use the holdout method, but to really get its power and, its limitations, we need to get a little more formal. And that all starts with a really critical distinction, the difference between evaluating a model and evaluating an algorithm.
So first up, we've got what's called the inner utility. You can think of this as a function that takes a single, fixed, already trained model, which in the lingo we call a hypothesis, and it just scores it on some test data. This is literally your accuracy, your F1 score, your AUC, whatever metric you're using. Simple as that. But here's where it gets interesting. This is the outer utility. Now, this function doesn't just score a model that's already made. No, it evaluates the entire learning algorithm. It's capturing the whole shebang. The algorithm takes in training data, it spits out a model, and then that model gets tested. And this little formula, it just ties it all together beautifully. The outer utility, GA, which is measuring our algorithm's performance, well, it's just the inner utility, KH, run on the test data. But, and this is the important part, the model being tested, H, is the direct result of our algorithm A being fed the training data Z-train. It's this beautiful nested function that captures that whole end-to-end process. Okay, so now that we have this formal tool for checking out an algorithm, what's the end game? What is the theoretical true score that something like cross-validation is even trying to find? This is our target right here, zeta-A. That E stands for expected value. This is the true average performance of our learning algorithm, GA, if, and this is a big if we could average it over every single possible train and test set that could ever be drawn from our data's distribution. It's like the perfect, you might say, godlike score for our algorithm. Of course, in reality, we can't test on every possible dataset. I mean, that's impossible. So, how does a method like k-fold cross-validation get us a decent estimate of that ideal value? Well, statistically speaking, it's what's known as an incomplete U-statistic. So a full, complete U-statistic would be the absolute dream estimator. It would mean taking every single possible train test split from our data, running our whole process, and averaging all the results. Yeah, not going to happen, right? That's computationally insane. So k-fold cross-validation is our practical, incomplete version. Instead of millions of splits, we just average over k of them. But here's the key, it still gives us an unbiased estimate of that ideal score, theta A. But this whole thing rests on a huge and often totally unspoken assumption. And that is that our training data and our test data are independent and identically distributed, or IID. We just assume they're all random draws from the exact same bucket of data.
But in the real world, that's just a fantasy. What if our goal is to predict on data that's fundamentally different from our training set? What if the test data isn't just more of the same? If that's the case, your standard cross-validation is not going to give you the answer you're looking for.
So this means we really need a shift in our thinking. Instead of just blindly assuming everything is IID, we can explicitly define or restrict the domain of our evaluation. We stop asking this kind of vague question, how well does it perform on more of the same stuff, and we start asking much more specific, much more useful questions like, how well does it perform on genuinely new data?
So how do we actually do that? Well, we use these domain restrictions to build some really powerful specialized evaluation methods that actually answer the questions we care about.
For instance, we could ask how our model performs on inputs it's never ever seen before. This is called off-training set inputs, or OTSI. And what we do is we set up our evaluation so that the input features in our test set are guaranteed to be totally separate from any inputs the model saw during training.
Or, and this one is really cool, we could ask how the model does when it has to predict target values or classes that were completely missing from the training set. This is off-training set outputs, or OTSO, and it forces our model to try and interpolate or extrapolate to labels it's never seen. And this is a perfect real-world example from a chemistry lab. So here the experimenters measured sensor readings for very specific concentrations of lead and cadmium. Look at how many of those measurements are stacked on the exact same output values. A standard cross-validation could easily cheat here, but an OTSO evaluation answers the much more practical question. Can my model actually predict for a new concentration that it wasn't explicitly trained on?
Now, this whole idea of data not being IID, it's not just about repeated measurements. It's a massive issue in any kind of geographical data. I mean, points that are close to each other aren't independent, right? A soil sample you take here is going to be super similar to one you take a meter away. It's called spatial autocorrelation, and it makes standard cross-validation dangerously optimistic.
And this just brilliantly illustrates the solution: spatial leave-one-out. When we want to test on a specific spot, that red dot, we don't just hold it out. We also ignore all the training data that falls within a certain radius around it. This forces the model to make its prediction based on data that's geographically distant. It answers that super practical question: how well does my model actually work when it has to predict at least, say, delta kilometers away from any known data point?
So this whole framework, this idea of defining the question before you start measuring, it's all about becoming a more honest estimator. It forces you to actually confront your assumptions and helps you spot those subtle but absolutely critical errors that can totally invalidate your results.
One of the most common traps, one of the biggest pitfalls, is data leakage during pre-processing. It's a perfect example of why this careful, step-by-step thinking matters so much. Can something as simple as standardizing your features completely break your entire evaluation? Oh yeah. The answer is a resounding yes.
You know, as a student in the lecture pointed out so perfectly, if you standardize your entire dataset before you do cross-validation, you've already made a massive error. Information from the test fold, its average, its standard deviation, has leaked into your training folds. You've given your model an unfair and totally unrealistic sneak peek at the answers.
So here it is, the correct way to do it. And the crucial point is this: your pre-processing steps have to be treated as part of the algorithm that's being evaluated inside each loop of the cross-validation. You fit your standardizer only on the training data for that specific fold, and then you use that same fitted standardizer to transform both your training data and your test data. This is how you prevent leakage. This is how you get an honest estimate of how your pipeline will perform on truly unseen data. At the end of the day, this framework isn't just a bunch of formulas. It's a whole new mindset. It forces you to ask the really important question: what unstated assumption is hiding in your evaluation pipeline?